Hello everyone, I would like to talk about your project, your final project. So first of all, let me show you where you are going to get your data from. All right, let's see. So it's going to be on this site, thanks to University of Sheffield. They have a very nice internet site on which they put some of these data, they put some data sets. So you can choose any of these data sets and do the comparison, which are basically t-tests, and also regression analysis. And I would like to show you a couple of examples of what you can do for these analysis. So let's see. All right, for instance, I'm going to be only talking about this crime data set because it has everything that we need here. So basically, I'm going to, like all the data sets, you are going to only need to concentrate on two files. One of them is the description file, in which you can see the variable names and their descriptions, and also some example questions are given here. You may use them or you don't need to use them. It's up to you. So, and this is the Excel file, which you should open. So let's see. First of all, to understand what this Excel file and what this data is about, it's a good idea to see where each variable lies. So for instance, crime data is the crime rate, number of offenses per million. It's going to be the first column here. Actually, I have colored this to orange. So it's going to be 45. So whatever the state name is, going to be 45.5 for each 1 million people. This state has that crime rate, and the second state is 42.3 and whatever. And actually, please note that the same variables here we have from A to N is repeated again here for the next, I think 10 or 11 or 12 of these columns. So basically the difference between this first and the second part lies is this part is 10 years. I mean, this part is 10 years after this sample. So it is, I don't know, 1980, it's going to be 1990 data. So you can do your analysis only related to this region. You can do your analysis only related to this region, or you can do some kind of pair tests, comparisons, things like that. It's up to your imagination. So let's see, for instance, second column is going to be youth, which is going to be young males, number of males aged between 18 and 25 per 1,000. So whether this state name is not given, whether it's a southern state or not. The education is how much education time, how many years up to age 25 is used in education, and there are all these variables. Some variables are a little bit unnecessary, like for instance, once wage is given, right? Or for instance, let's see a more familiar example, easy to understand. For example, mature unemployment or youth unemployment. All right, youth unemployment is indeed a continuous variable. Right, let's see exactly what it is. Youth unemployment, number of males age per 1,000. So there are 22 males, for instance, in this state per 1,000, which are, I'm sorry, there are 80 or about 100, let's say, youths per 1,000. So it's 10% of the youths approximately are unemployed in those two states. This is what it means. And high youth employment is whatever the high corresponds to that state. I don't know. This variable actually corresponds to that. So that 1, 1, and 0 is, as I said, whatever the criterion for high employment, they have used this criteria for that state and converted to high youth unemployment. I don't think it's a very good idea to use this variable, those kind of variables which are derived from the already existing continuous values. It's up to you, but that's my point. Please note that I don't mean that it's not a, I don't want to say that it's not a good idea to use binary or categorical variables like those. Actually, this variable is actually very informative. I'm going to talk about that. The example is on that. You can use this, but as I said, if there is a continuous variable, and from that continuous variable, if you derive another variable, it's a better idea not to use it. That's what I'm trying to say. Okay, so you can do what type of analysis? If you have usually categorical variables, discrete variables, for instance, we called it in our lectures, usually you can do a comparison test. What do I mean by that? Here, for instance, the crime rate seems to be the most important variable. For instance, a very typical comparison test would be whether the state is a southern state or not. So not a southern state. Southern state is 0, southern state is 1. So you can classify those crime rates into two, whether they are from a southern state or not, and then perform, for instance, a comparison between those two. And how are we going to perform this comparison? First of all, we can do descriptive statistics, just like we did in the very first chapter. Then we are going to do a much more formal hypothesis test. So basically, it's going to be an independent t-test. Or you can do, for instance, note that these are all continuous, or tests need, for tests, we need two different groups. Yeah. For instance, here you can use a t-test, whether the states which correspond to 1, which have high youth employment, their crime rate differs from whether the state has low youth unemployment, which the states which correspond to 0 here. But the thing that I don't like it here, because there is already a continuous data here, so I don't need that additional thing. But you can do, for instance, something like this. For instance, when it comes to youth unemployment, you can say that I'm going to divide the youth unemployment into 2, dividing from 100. So those below 100 and those above 100. You can divide this youth unemployment into 2. Then those below 100 is going to correspond to group 1. So the group 1 crime rate, does it differ from group 2, which consists of youth unemployment, which are above 100? So you can form these kind of groups. Actually, in the very first project, you have already done that. Maybe you can go back and see what you have done. Maybe the groups are already formed, but the basic idea was there. Either you can directly find the categorical variables and use the categories to form into groups, and use the group crime rate in those two groups and compare them. Or you can convert continuous variables. For instance, when it comes to state size, you may say that, for instance, I'm going to divide the states into 2. So the state size which are below, so whatever the unit of that, I don't want to go into that. That's not that much important. While you are preparing the report, it's important, but not for me. For instance, state sizes below 50 is going to correspond to group 1, and state sizes above 50 is going to correspond to group 2. So the group 1 crime rates are going to be compared with group 2 crime rates. That's one option. And when it comes to regression analysis, you can directly use any of those two columns. While using crime rate as the y value, the response variable, the dependent variable is a good idea, because we are especially interested here in this one. And for independent variable, you can choose any of these x. However, please note that this one is a strictly observational study. So it is very questionable which one is x, which one is y. So in this case, we are going to take this always as y, but please do not draw any causality connections, right? That's an important thing. We don't know where the causality lies or causality lies. There may be confounding variables, and also I'm going to talk about that in the example I'm going to try to So for instance, let's see. My Matlab here, written some code. So what you are supposed to do is indeed something like this. First, I take the data, it is crime XLSX. This is the name of the file I have given, and I load it to Matlab. Note that txt here will correspond to the first row here, and data will correspond to the rest of the numerical data. Size data, for instance, I'm going to see that this corresponds to 47 states and 27 columns. All right, so what I do is I'm going to first of all do an hypothesis test on this part of the data. Note that you can do the very same thing on the second part of the data, because the only difference between these two sets are they are 10 years apart. All right, so what I do is I take, let's say, X here. I'm going to do an hypothesis. So X and Y will not correspond to independent and dependent variables. They are just two sets of variables. They may be, I could have called them X1 and X2. So I take the first column here, the crime rate, right? I could have easily, for instance, to take the crime rate data, I can write data 1 here. So I'm going to be taking all of the first column values, which are going to be the crime rates. But what I do is this, I divide it into two. What do I mean by that? I check whether the third column, which is the southern part, right? Whether it is equal to 0 or 1. Whether if it's equal to 0, let's call it north. If it's equal to 1, let's call it south. So X would be here equal to the crime rates, which are the south states, and Y here will correspond to the crime rates for the I'm sorry, X will correspond to crime rates for the north states or the non-southern states, and Y will correspond to the crime rates for the southern states. Actually, it's a bit difficult to say the whole thing again and again. All right, let's take that. So if I take the length and if I display them, all right, number of non-southern states is 31, number of southern states is 16. So first of all, we should have an idea about what's going on. Then what I do is something that we have skipped in our lecture. We assume that since these are small sets of values, we usually assume in our lectures they are normal distributed, but indeed, are they normal distributed? So there is a normal plot on Matlab to check that, and please see in your textbook or in other sources using internet or whatever, what normal probability plot is. So for X, so which are the non-southern states, the price, I'm sorry, not the price, what was that? The crime, yeah. The crime data is like this, and for the southern states the crime data is like that. As you can see, well, actually maybe this normal probability plot is alien to, I think I should have explained this in one of the bonus lectures. I cannot remember exactly. If I had, probably I'm going to add this to the description of this specific video. Anyway, well, this looks pretty much normal. This is slightly non-normal, but this I think is excusable. So another thing that you should do is, if how we read this normal probability plots, and if not normal, what do we do? Just search on the internet and see what people do. Basically, in a nutshell, this is not very non-normal, so we can continue. So the simplest thing that we can do here is draw a box plot of these two states, of these two types of states, non-southern and southern states. So these are the crime rates, these are non-southern states, these are southern states, and these are the box plots. But note that box plot is a descriptive only statistic. all right, a graphical descriptive statistic, we need to make an inference here, a more rigorous inference. We need to do an hypothesis test. A minor point here, actually, maybe I should add this in a bonus video, or maybe I should not say anything about that. So I'm going to just say it, and I'm going to leave for curious souls. It is a little bit questionable from a rigorous statistical point of view whether you can conduct an hypothesis test here or not. But I'm going to leave it. Just take this as a learning exercise. So anyway, assuming that we can conduct a hypothesis test here to make an inference, not just be content with this box plot, we have to compare these two groups. And please also note that you can compare whether the variance of these two types of states, they are equal to each other or not. That may be another comparison, right? But here I think I have only compared the population. Anyway, so the very first thing, let this stay here. Let me also write here the average values in those two types of states. So crime rate in non-southern states per million is 104, and in southern states it is 100, slightly lower. And note that we have 31 non-southern states and 16 southern states. Actually, one of the reasons why this seems smaller, the range here seems smaller, is because we have a smaller number of states here. That's a tricky thing. Actual standard deviation. Now, I'm a little bit, since this is the last project that you are supposed to do, I'm going a little bit about the introductory statistical level, introduction to statistics level, let me say. One may think at very first sight that this has lower variance, and it maybe probably have lower variance. On the other hand, the sample size may be also deceiving. Note that if you have a larger sample size, the range is expected to be larger. What we see here is not standard deviation, it's actually range. Please be careful about that. And the reason why this range is higher than this range, one of the reasons at least, maybe because this has a larger sample size. Because usually what I can see, especially from a box plot, is not standard deviation, is the range, right? All right. But I believe standard deviation here of this group is also smaller because this interquartile range is also smaller. And this whole thing, we can easily calculate and do a hypothesis test here, but that's not what I'm going to do. Anyway, now the hypothesis test of two groups, independent hypothesis test, is conducted by this command. Please write help and see what each of these means. I have assumed that the variance of two groups are unequal and conduct the hypothesis test. Now, when you do that, I expect you to also do the calculation by a pen and also calculate, or using Matlab, but using the equations, and see that you get the same result. Here, H is the result of the hypothesis test. Null hypothesis is not rejected. So what is the null hypothesis here? Let's see what the null hypothesis here is. So if we define X1 is the crime rate in a non-southern state, and X2 crime rate in a southern state. Of course, this is with respect to United States. And mean one is going to be population mean of 1, and mean 2 is population mean of 2. My null hypothesis is mu1 is equal to mu2, and alternative hypothesis is these two are not equal to each other. And X1 is found to be equal to 103 something. Let's see what was the value. Now 104, about 104, and x2 is equal to 100.6 or 7. Let me also write it with one significant figure. Yeah, I mean 4 significant figure, 1 significant figure after decimal point. So what you should do is t0 is equal to x1 minus x2 minus 0 over then standard deviation, blah, blah, kind of thing, and come up with the result. So if you do this, this says that hypothesis is not rejected. P-value is found to be equal to 0.70. Now, if you write stats here, the t-stat here is found to be equal to 0.40. It's a very low value. That's why you have such a high p-value here. Degree of freedom is found, and also, as you can see, it's not a integer, because we are talking about, or at least I conducted this test with assuming unequal variances, and also this will also give us a confidence interval here. So this difference, which is mu1 minus mu2, is supposed to lie between 19.4 with 95% confidence level, or at 95% confidence level. And since it contains 0, we cannot reject the null hypothesis. So there is no reason to suspect that the crime rates in those two Saturn and non-Saturn states differ in United States. As you can see, although the Saturn states have a smaller crime rate, you cannot generally say that Southern states has a smaller or different, the crime rate is different. All right, now let's see, what did I do? Yeah, the second one is a little bit, this is one thing that you could have done, but of course, since I did this example, you cannot do this. The second one is a little bit interesting. Now, these crime rates are 10 years apart. So what I did is something like this. So first, let me write it here. So X1 is again Saturn, non-Saturn, or non. But there is another variable here. This is at 0 time, and X1 and 10, X2 at 10 also. So this is non-Saturn 10 years later. And we have the same thing here, Saturn 10 years later. So what I do is this. I define a D1. D1 is X1 10 minus X1 0. So what happened in non-Saturn states? So the crime rate increase in non-Saturn states. This is D1. And note that if you only concentrate on this value, for instance, that would be a pair t-test, because that may be greater than 0, less than 0. Because why do I call it an increase? Because if it's a positive number, let's say this is equal to 5, this is equal to 4, then the difference is going to be 1. So 1 unit increase in 10 years. And if I do the same thing, it's going to be, this time it is X2 10 minus X2 0. It is crime rate increase, of course, in 10 years in Saturn states. So I'm going to find those two statistics. Then what I'm going to do is, this is a little bit interesting. If I call mu d, or let me do it something like this, then I'm going to define population parameters here. Mu d1 is population mean of d1, and mu d2 is population mean of d2. So here now the question is whether mu d1 is equal to mu d2 or mu d1 is not equal to mu d2. So that's an interesting statistic. It's not exactly a comparison of the crime rates in those two types of states, but the change of crime rates within those 10 years, whether that change is different in those two types of states. I may call this. That's why I need to define all of this and make sure that it makes sense here. So this is a comparison of not the crime rates, but the change in crime rates in 10 years. So if I do that, so what did I do here? That's what I call test two. I call this time, I take again the non-Saturn states, the row part, and for the columns, I take the first and the 15 columns. So why do I take them? The first column is crime rate and the 15 column is crime rate after 10 years. All right, then what I do is I take the difference from the second column to the first. This is how you can do that. Just type help diff and see how this is used. So this is going to be the single column. So if I do that, for instance, I'm going to be finding X values. And these are how crime rates have changed in those non-Saturn states. Note that the order is not random, but the people who have prepared this Excel file have prepared this such that the negatively crime or decreasing crime rates, the states are first typed, then the states with increasing or the usually increasing crime rates are written. So I do the very same thing here, but this time for Southern states. And then I'm going to now see Southern states, I have these. Now note that if there were no change within 10 years, both would have given 0. So, and what I'm comparing is, I repeat again, the change in those crime rates. Now, since I'm going to be comparing those two, I need to make sure that again, whether they are normal or not. So I'm going to check these X and Y values. So let's see again. Well, these ones, both of them are not very normal, but that's not also very non-normal, I may say. So we can continue with the t-test. So what I do is again draw box plot. Note that this time box plot is around 0, right? We have these positive values and we have these negative values here. So basically I compare these two. So again, I may write this. So increase in crime rates of non-Saturn cities is minus 1.3, right? Minus 1.03. Therefore, the crime rate has decreased by 1.04 units people per or incident per 1 million people, as far as I can remember. And increasing crime rates in Southern states has decreased by 0.16 incidents per people. So what I do here is this time I do this test. Note that this is going to be again an independent t-test, and that's the tricky part, right? I have defined these D1 and D2 like a paired t-test kind of definition, but now here I conduct, once I obtain these D values, I conduct an independent t-test, and this is the command. Independent t-test, and let's see what the results are. Again, the null hypothesis is not rejected. Therefore, this is not rejected. So we cannot say that the rate or the difference within those 10 years in the crime rates in both the northern or the non-Saturn and Saturn states are significantly, statistically significant from each other. Let's see what the p-value is. A very high value again. P-stat is minus 0.28, a very low value. And why is it minus? It is minus because this value is smaller than this one, right? And confidence interval here is between minus 0.7 and 5. This may change since it includes 0. We cannot say that there is significant difference. So that could have been a second test. So it's up to your imagination to come up with different tests. And the third test is the one I have already written here. What about, now note that this only checks whether there is a difference in the change of crime rates between those two types of states. This does not say that there is no difference in the crime rates in the non-Saturn and the Saturn states. Each D1 and D2, they may have significant changes, but the difference between them, or when you compare those differences, you may not see any difference between these differences. It's a bit tricky, as you can see. Maybe I shouldn't come up with that much confusing stuff, but once you get the idea, I think your imagination will open up. Anyway, so what I'm going to do is a very simple test right now. I'm going to see whether D1, or the expected value of D1, I may say, let's call it new D1, whether it's equal to 0 or it's not equal to 0. So here it means whether the non-Saturn, the non-Saturn states, their crime rates have changed within 10 years or not. In this case, I do not care about this part. And this is exactly a paired t-test. Why do I call it a paired t-test? Because I have x1 values and I have x2 values, and I have subtracted them here. So basically, once you have already subtracted the values and obtained the values, note that this is simply a t-test, whether the population mean of these values may be equal to 0 or not test. So in this case, I feed the values of x here, which corresponds to the first difference here, right, of the non-Saturn states. So where am I here? Yeah. So I use the command t-test for this case. So this 0 is to test whether the mean of this x can be equal to 0 or not. And I use a single, this time already, although I said not equal to 0, I have used this one, right? So whether the crime rate has decreased or whether it is constant. This is basically, so the question here is whether crime rate in non-Saturn cities or states constant or decreased. Constants correspond to this hypothesis test, and decreased correspond to this hypothesis, the alternative hypothesis. So basically, this is what we do. Let's see. Again, null hypothesis not rejected. P-value is slightly smaller this time, but still. This, as you can see, this is a one-sided test. That's why from -infinity to 2.55, you were, some of you were at least a little bit confused about which value to take, or whether upper or lower bound to take. Here, as you can see, we are interested in d value, smaller upper bound, probability is equal to 0.095. So what we obtain at the end from -infinity to upper bound here. So if this upper bound contains 0, then we won't be able to reject the null hypothesis, and that's exactly what happens here. And when you you can see that this stat is -0.5. Although this is a negative value, still you cannot reject it because it's not statistically significant, and degree of freedom is 30. And where does 30 come from? It comes from the length of x. Length of x is 31 observations, so one less here, it is 30 here, and standard deviation is 11.75. So these are three different things, or three different comparisons that you could have done with this data set. As I try to explain in your project, there's a PDF file which I am going to post on Moodle. You are expected to do 2 of these tests, either on the same data using different variables or different combinations, whatever you would like to do. You may also conduct proportional equality of proportions or comparison of population proportions, and we may also check the equality of variances. I have only shown you tests related to equality of means and t-test. It's up to you, but you have to use Matlab and the corresponding command from the statistical toolbox. And I expect you to do, as I said, tests. It may be from the same data sets or 2 different data sets, and from each of them you may conduct 1 t-test or 1 comparison test. It is always a good idea, as I've done here, to combine descriptive statistics with also the more formal inferential statistics. So first plot an histogram or a box plot or things like that. Try to do the comparison there, then, or maybe equal to 0 thing. It's not always a comparison, right? For instance, for this test, it's not comparison, but it is indeed is equal to 0 or not test. So for this test, maybe a better diagram could have been an histogram of X. Let's see. So that would be the descriptive statistics of this data. As you can see, it's very much scattered around 0. Maybe I can use, for instance, 6. Yeah. And the more formal statistics of or statistical procedure to test whether mean can be equal to 0 is, as I've shown you, t-test. But descriptive statistic also gives you a visual perspective of what's going on. So try to combine them and come up with a result, actually 2 different tests. And the other thing that I expect you to do is linear regression. Here I have given only 1 example here because it's a bit more longer. So when it comes to linear regression, you have to choose 2 continuous variables. So Saturn or high youth unemployment cannot be used for linear regression, since we have not covered logistic regression. So choose any 2 variables, and we are going to call this crime rate Y and the other variable as X, but do not take much too seriously X and Y as independent and dependent variables, because X is not indeed independent and the other does not depend on Y kind of thing. There is a much more complicated causality here. So causality cannot be extracted from this data, but only correlation. Okay, so what I did was I have taken the 5th column, which is expenditure year. All right, and let's see what this is. Expenditures per capita, expenditure on police. So how much expenditure is invested for police forces, something like that, probably for that state. And I'm going to try to find a relation to this variable with the crime rate. And you may probably think that there may be some much more related variables. Please try to come up with your own conclusions and search for it. You are going to see that for many of the variables, you are not going to see the correlation that you expect to see. One of the reasons, maybe because this data is very limited. The second one is this actually needs a multivariable regression analysis, not a simple linear regression. But maybe most important of all, most of the things that you expect are related with the misinformation that you have from your social life. And when it comes to statistics and real data, most of them do not fit with your expectations. But it's very difficult to overcome those biases and accept the results from the numbers. But that's another story that I would not go into. Anyway, so I have taken these 2 X and Y values, right? So first of all, to give you an idea that we are on the right track, that there seems to be a relation between X and Y, it's always a good idea to show X and Y. Here, X is, as I said, police expenditure per year, probably some $1 million or whatever. And okay, let's not say whatever, but let's see what it is exactly. Expenditure per capita. In it, I don't know the exact unit. Anyway, so as expenditure on police increases, then crime rate increases. As I said, this does not mean a causality. Do not automatically say there is a causality between those. So as there is more police, there is more crime kind of thing. Actually, it may be opposite. Just because you put this on y-axis, it doesn't mean that there is causality here from this part. This may be from here to here. There is more crime rate, then there is more expenditure on police, or they may depend on confounding variables. Like, for instance, there is some economical issues, there are some cultural issues, whatever, which both stems or which both results, yields high crime rate and high police investment kind of thing, which are related to other branches of science, which of course we are not going to go into. So anyway, there seems to be a relation between those two variables. So what we are going to do here is the classical, or let me say not the classical, but the machine learning approach. We are not going to take the whole data and we are not going to fit a line to that data. What we are going to do is we are going to divide the data into two, a training data and testing data, and then do a couple of things. Let's see. So first I find the number of samples. I have 47 samples. That's great. Now I take the 3.5 of these values, which are equal to 28, and I'm going to use the 28 points. It's slightly more than the half of these data points for training for coming up with the model. Then I'm going to use this model for testing unseen data. So what I do here is I randomly sample from these 47 data points. Rand sample is the command on Matlab. Please help see how these commands work. And I'm going to take 28 of them. And these will correspond to training data points. So these are going to be indices that I'm going to be using. So these indices are taken from X and Y values. And they are stored in X train and Y train. Then the test indices would be the indices which I have not taken previously. So for instance, there is no 2 here as far as I can see. Yeah, for instance, it's going to be 2. The second observation is going to be put in test data, and the 3, and I guess 5, and it goes like this. So what I need to do is I need to find the difference of the set which goes from 1 to 47 and this set. So this is set diff command on Matlab, and again type help and see how it works. So indices of test data would be this. So indices of test would be, yeah, these points. So X test and Y test would be those. Then, okay, what I assume is I have this data here. These are my training data. For the time being, I don't know the other states. So these states will be of these 28 states here, from 30 to 22, all these states here. These states are not plotted here. I assume that for the time being, I do not know. So the simplest way of, as far as I'm concerned, of constructing a linear model on Matlab is by using this command, X train, Y train, and type linear. And when I type that, all the information that we need is given. So model is modeled, as you are going to see how in a couple of minutes how we are going to be using this model. All right, so this is beta 0 hat and this is beta 1 hat. Note that standard errors and the corresponding t-stat and p-values are also given. Now, the very first thing that you should check whether this regression is significant. Indeed, this p-value gives this. Actually, these are all in our lecture notes. To check whether a regression is significant or not, we check the significance of beta 1, right? This value. and the p-value, if it is sufficiently small, shows us that the regression is significant, which means there is a relation between x and y. And here, for this case, expenditure on police and the crime rate. And note that the very same p-value here is written here. This is by an f-test, which I haven't shown you when it comes to the regression part. We haven't covered that, but the regression, significance of regression is indeed when you have a simple linear regression, by the way. If you have more than one variable, that's another story which we haven't covered. These two values are going to be equal to each other. And the R-square value is 0.45, which is not very high, but which is not also very bad. The reason is very simple, because when you draw this, actually, where is our drawing? Yeah, when we put a straight line here, it's going to be a little bit of these points are going to be a little bit scattered around the line. There's nothing that that line can do. It cannot draw these points back on itself. So it doesn't have such a power. So this is the best that you can do. All right. Now what we usually want to do is draw the fitted line on this figure. What we do is going to be very simple. I take the minimum value, find the minimum value in this X-train data, which is going to be here, I think. So it's going to be 40 something. And find the maximum value here, which is going to be 100, whatever it is, 120, or I'm sorry, 166, right? Or you can manually enter these values, whatever. Then I predict the outcome of this model at these values, right? And then I plot a straight line using those points. So what I do is, so this is our fitted line here. So for instance, if you would like to estimate the crime rate when we have an expenditure of police equal to 100, then you come here, and of course it doesn't show it because it actually draws this line only using these 2 points here. On this one and this one is found, right? Yeah, y hat is actually equal to these values. And what are these values? These are equal to when mean x is mean x and mean y. Max x. So when x is equal to 45, y hat is going to be equal to 81. This is what it says. And when max x is equal to 166, right? This value. Meanwhile, I'm sorry, the corresponding y value is going to be 140 something, 146. And between those two, we have a straight line. And you can, of course, do this and see. For instance, when we have 100, it's about 110.6, something like this. Of course, you can directly find it using predict. Right, 100, 110 point something. Yeah. Now, this is for only fitting the data. Now comes the testing part. First, all right, these are the testing points which I haven't used in my figure, in my model yet. So why do you may easily ask, why did I do this, separate these into two? Because now this is something we have never covered, but it's always a good idea to also to slowly go into or step into machine learning. The idea in machine learning is you have a finite data. From that finite data, come up with a learner or a machine which is going to use these data usually to come up with a model, but in some cases it's not going to come up with a model, but somehow use this data for unseen data, prediction of unseen data. This is basically what supervised learning is. So what do I mean unseen data? So these data are given, the x and y values of the historical data is given to the machine. It takes these data, do whatever it wants to do. And once it says, okay, I'm ready, a new x value comes, not y. What do I mean by x value? For instance, x is equal to, let's see what x test is equal to. The first value is 55. So when x is equal to 55, a specific y test value is also there but unknown yet. For instance, you need to measure this value or wait for this value for this specific case. We don't know how many crimes is going to happen. Let's say that for that current year, we know how much investment has been given to the police, but it takes 1 year for the whole crimes to occur in that city, state, whatever. So we don't know the y value yet. At the beginning of the year, given that information, given the previous information, and that specific information about the police, which is equal to 55, can this machine predict what the crime rate is going to be? Yes, that's what it does. So predict model, I'm using this model with 55. It says it's going to be 86, and the real value is 52. So what I do here is, this only for a specific year, I use this command for all of the X test values, right? Only the police investments are known for different states. But not only I do point predictions with 95% confidence interval, I determine a prediction interval. And now I also show on the same figure with error bars. Now see it from this perspective, and instead of these squared are, or these points, circular points are for the training data, whereas the squared samples are for testing data. So for each test data, the estimate is on the line. So here, for instance, this is the estimate, and this is the prediction interval. It says that, for instance, for this specific X value, whatever that X value is equal to 47, our model, our machine, let's call it machine so that it is, sounds cooler. It predicts the state's crime average or crime value to be equal to 82. Indeed, its true value at the end of the year comes about, if I can, it's difficult to show. I think I should erase this, but as you can see, it is slightly below 60. But on the other hand, it says that there is that much of prediction error that I can commit. So of course, it's not going to exactly lie on this line here, but is it in the 95% prediction interval? Yes. So it's okay. The second point, it's here. As you can see, almost all of them, that's a very actually nice demonstration of 95% confidence interval, except one. All of them are within confidence intervals. You may easily say that, okay, why is this outside of confidence interval? Because it's 95% confidence interval. 95% means that for 1 out of 20, you expect the confidence interval would not work. So here, how many samples do we have in the test sample? Let's see, X test. 19. Well, it's a coincidence that 20 and 19 seems to be. So anyway, when you put this 95% or significance level 0.5, it is not surprising that one of them is outside the confidence limits. On the other hand, if I put here 0.01, for instance, which is 99% confidence interval, then let's see. All right, when we have 99% confidence interval, note that the only thing that has changed are the width of these confidence intervals. Now they are all within confidence intervals, because for 19 test points, it's a bit of a low probable that they are going to be outside the and all of them would be prediction interval, not confidence interval, because we are talking about individual predictions. So this is the idea, what I expect you to do. And one thing that we do is we at the end find root mean square error test values. What do I mean by that? If you look into this formula, it is the difference between the predicted and the test values squared mean squared root. That this is actually very similar to this value. For training set, we find here the sigma square values. In square root, it is sigma hat value here. What we call root mean square is sigma hat value that we compute. So the total error divided by n minus 2. Here I find this quantity for total prediction error divided by n. So I expect these two values should be close to each other. If this is very much higher compared to this error here, then my model shows that my model is not working correctly. Because in the training data, it is a small error, but in the test data, it is a very large error. Therefore, it doesn't work as it's supposed to be working. Think about this training error. You go to market to buy something and they show you the equipment and it seems to work, and when you go home and let's say it's a vacuum cleaner, you expect a very similar performance. If your performance decays significantly, then you probably take the equipment and take it back to the market or wherever you have bought it and say that there is something wrong with that. And this is very similar with the training data. The machine comes up with a model. So whatever the performance that is supposed to have on with the training data, you expect for the future data to have a similar performance. So that whole thing is one linear regression analysis, but it's an example of a linear regression analysis that I expect you to do. I expect you to do two of these linear regression analysis using two different variables. In some cases, there may be insignificant variables, right? As I said, you may be surprised to see, for instance, okay, let me give an idea. I'm sure that since the popular culture gives people that more education, less crime rate kind of thing, right? If we regress the fourth column with the first one, let's see what we are going to obtain. All right. Let me first get rid of the, only concentrate on training. All right. First of all, the model, that is not expenditure on policy anymore. So this is, get rid of this. Where is expenditure on policy? This is not expenditure on policy anymore. This is education. And what does education here mean? Let's see what education is. Education time up to 25. All right. Education time up to 25. So how many years of education? All right. Model insignificant, right? 0.25 p-value. Still, if you would like to see what the relation is, education time, as it increases, crime rate also seems to be increasing. And the R square is 28.5. Let's see. Root mean square error test is pretty much close. And let's see the relation. Yeah, they are all within 99 also percent limits. And this is probably contrary to our expectation, but that's when it comes to numbers and reality, it may clash with the popular and the internet culture. All right, that's all.